Swayam Prabha. Digital India. Educated India.
So, in this lecture I want to talk about something called Ethereum rollups, which are a scaling technology for Ethereum. So, why do we need to scale Ethereum? So, each operation on Ethereum costs some gas, like we saw yesterday. So, the minimum transaction gas cost is 21,000 gas, and suppose you want to do Ethereum transfer, that also costs 21,000 gas. If you want to do a token transfer, so ERC20 is a token you can create on Ethereum, so that costs 65,000 gas, but the minimum is always 21k, and the block gas limit in Ethereum is 30 million gas. So Ethereum does not have a block size limit, it has a gas limit. It limits the total number of operations via the gas. So if I just look at Ethereum transfers, so if I divide this 30 million by 21,000, each Ethereum block can accommodate about 1400 Ethereum transfers, and an Ethereum interblock time in Ethereum is about 13 seconds, so that will work out to 109 Ethereum transfers per second. But in practice, if you look at the historical data, the actual throughput, the number of transactions per second in Ethereum is actually only 15 transactions per second. So that is very low if we want Ethereum to support very diverse applications. And what happens is that whenever there is a high demand for Ethereum block space, suppose there is an auction or there is an NFT which is being auctioned off, then people compete in the auction, and they want their transactions to get included in the block, so they end up paying higher transaction fees, because the transaction fees goes to the miner, so the miner will always include transactions which will pay a higher fees to them, so the transaction fees goes high. So how do we increase Ethereum's throughput? That is, how do we increase the number of transactions which an Ethereum block can accommodate? So there was a previous attempt maybe 4-5 years ago. It was called Plasma. The main idea is that we will move the computation and the state off chain. So what do I mean by computation? So if I have a computation which happens in an Ethereum transaction, then I have to pay gas, which is accounted for in the Ethereum block. But suppose I have a separate blockchain, I'll have another blockchain where I'll do the computation, and that separate blockchain will have also the state variables. So this is called moving the state and computation off chain. You are having a separate blockchain where you do the computation, but what will be stored on Ethereum is only the state root. The state root is the Merkle root of the world state. So you have a separate blockchain, it has its own world state, and you compute a Merkle root of all the state in that separate blockchain, and you store that on Ethereum. This attempt was called Plasma, this idea was called Plasma, but the problem was that you needed to trust the Plasma operator. So the person or the entity which is running that separate blockchain is called the operator of the Plasma. So if they have control over the state and the computation, and if they withhold the data which is involved in that separate blockchain, the Plasma blockchain, then users may not be able to withdraw their assets. So the way the workflow would be is that I want cheaper transaction fees, I can't use main Ethereum, so I will move my assets first from main Ethereum to the Plasma blockchain, then I am at the mercy of the Plasma operator to guarantee something called data availability. So since the state of my assets, once I move it to the Plasma blockchain, is in the another blockchain, that operator of that blockchain has to make that data available. So data availability is a problem. So because of this problem of data availability, it was not solved. People came up with various kinds of mechanisms to solve this data availability problem. What if the Plasma operator disappears, or if they stops operating their node? Because there is no mining on the Plasma blockchain, so there is no incentive for people to run that Plasma blockchain or maintain that Plasma blockchain. So there was no clean solution to this problem. So there was limited market adoption, Plasma never took off, but what did take off is something called a rollup. The idea of a rollup is that same as Plasma, we will move the computation and state off chain, but the data which is going to be in the rollup blockchain, the second blockchain, that will be posted on Ethereum as something called call data. So what is this call data? I will have an example in the next slide. So call data is actually arguments to smart contract method calls. It is accessible in the current method call. So if I call some function like mint, the arguments are accessible in the current method call, but they are not accessible later to other method calls. But they can be read from the Ethereum logs. And call data is cheaper, and that enables you to reduce the cost of storing the data, the state data on the Ethereum blockchain. So the main idea of rollups is that for data availability, you will use the main Ethereum blockchain, but you will use it by you'll use the call data in the Ethereum blockchain to ensure data availability. And then what is stored on the main blockchain is again the state roots. Like Plasma, you will store the state root. You will just store like a Merkle hash, some 32 bytes of the complete state which is stored on the rollup on the second blockchain. But how do we know that the state root is correct? Because if we move the computation and state off chain, suppose I have some account balances which are to be stored, and then I store only the root on the Ethereum blockchain, then how do I ensure that that root is correct? So there are two mechanisms. There are two types of rollups which are differ in the mechanism to ensure correctness of the state root. One mechanism is called a fault proof, and the other mechanism is called validity proof. So we will see more about these two mechanisms in the subsequent slides. The disadvantage of rollups is that the user experience is slightly degraded. And what is the degradation? Certain operations take more time. Certain operations are as fast as main Ethereum, but some operations will take more time. I will explain which of these operations get delayed. So let us look at this call data. So what is this call data? So in Ethereum contracts, there are three types of data locations. One is called storage, where contract state variables are stored. Then there is something called memory, which persists only during the current method execution, and then after that it is not accessible by any contract method. And then there is third one is call data, which are read-only locations in the function arguments. So here is an example. So this contract is called data locations. So this array of unsigned integers called ARR, this is a storage array. So this is the first type of data location. So this will persist as long as this contract exists. So this will persist. This array can be accessed in all the methods which are called even later. This second example, this array here, which is the argument to this function g, that is a memory array. So this memory array underscore r will be accessible only during this function call. This is the second type of memory location. And then this argument will not be accessible later if I call g again, or if I call h, it will not be accessible. It is only accessible in the current method call. So it is not a persistent memory. It will disappear after the current method call completes, after this function call completes. Then the third type of location is call data. If you see this h function, this I am annotating this argument as call data. So this is accessible only in the current method call. It can't be accessed in the later method calls. But one thing about this is that its cost is lower. So what is the cost of the different types of data? Storage. If I have to store a byte in this kind of memory, a storage array which persists forever as long as the contract is operational, that costs about 690 gas per byte. Memory, it scales quadratically with the number of 32 byte words. So as the number of 32 byte words you store keeps increasing, then it will scale quadratically. So it becomes expensive once you have enough number of words in the memory. And then call data is 16 gas per non-zero byte and 4 gas per 0 byte. So if you compare 690 gas to 16 bytes, it's like almost like an order of magnitude lower. So call data is much cheaper to store information, but the disadvantage of call data is that call data cannot be accessed after the method call is completed. So this call data will be available only during this method call, but in later method calls it's not accessible. But what does happen is whenever a method is called, the function call is recorded in something called the Ethereum logs. So every Ethereum node will have this call data array in its logs. So anybody who is running an Ethereum node can recover this data. So the idea of rollups is that let us store the state which is required, which is the state root will be stored in storage. So state root will be stored in some variable like this, but the pre-image of that state root. So what data needs to be hashed to get that state root, that I will store in this call data because it is cheaper. It's only 16 gas per non-zero byte. And there are proposals which are being in Ethereum. There is a proposal to reduce the cost of this call data even further, and the main motivation is to enable rollups to scale even more. So call data is much cheaper than storage, and contract methods can only access call data in the current call, not past calls. But what the rollups will do is we'll store the essential state in storage, that is like the state root, and sometimes we'll store like account balances. But everything else which is needed to justify those account balances, they will not be stored in storage, they will be stored in call data. So that is the main idea. And so how popular are rollups? So here is a screenshot from a website called l2beat.com. It gives a graph of the total value locked in Ethereum layer 2. So as I mentioned in the context of Plasma, before you can do transactions on layer 2, you have to move your layer 1 assets to layer 2. Layer 1 assets can be like Ether, or it can be your ERC20, some tokens which you have created, it can even be NFTs. So you have to move your assets to layer 2 by doing a layer 1 transaction on Ethereum, and then after that then you can transact on layer 2 at a much cheaper cost. So this graph is showing for the past so from November 2019 to December 2022, it is showing you the total value locked. The y-axis is in billions of dollars, and the current on December 13th 2022, the total value locked was $4.4 billion. So it has fluctuated, it has increased, there was a spike and then it has fluctuated. It is reduced from the peak. At the peak it was close to $7 billion or close to $8 billion, and now it's at $4.4 billion. And if this is a list of rollup projects which are and their corresponding total value locked. TVL is the total value locked. So here is something called Arbitrum 1. That is the most popular rollup in terms of total value locked. It has $2.33 billion worth of assets in it. And if you notice the last column, under technology, it is listed as something called an optimistic rollup. We will go into these details about what is an optimistic rollup. And then the second one is also an optimistic rollup, it's called Optimism, and its total value locked is about $1.2 billion. And the third and fourth are listed as ZK rollups. ZK here stands for zero knowledge. So ZK rollups use something called zero knowledge proofs, which I hope Manoj has introduced. They use zero knowledge proofs to ensure the validity of the state root which is stored in the main Ethereum main chain. So DYDX is a decentralized exchange, and Loopring is it is a rollup which allows you to do regular transactions, payments, and also token transfers and swaps. So this is also a ZK rollup. And then there are some other types of technologies here. This is something called an optimistic chain and a Validium, and this is ZK Sync is also a ZK rollup. So ZK rollups are also called validity rollups because they give a validity proof of the state root which is stored on the Ethereum blockchain. But how cheap are Ethereum layer 2s? So layer 2s rollups are called layer 2s because Ethereum is considered layer 1, and layer 2s are separate blockchains which have their own set of transactions and blocks, but it's cheaper to use them. So how cheap are they? So here is a screenshot of the fees on layer 2 which I took yesterday. So if you see the last row, it gives you the fee for sending Ethereum on the Ethereum main chain and for swapping tokens on Ethereum main chain. So these are types of transactions. Sending Ethereum is just transfer Ether to from one address to the other, and the swap of tokens is that maybe I have one kind of token, I want to swap it for another. So that the prices are like 41 cents and $2 on main Ethereum. But if you look at these rollups which are there, so Loopring is for sending Ethereum, it costs only 1 cent, which is like 40 times cheaper than mainnet Ethereum. Then there are some other examples like ZK Sync costs 3 cents, Arbitrum 1 costs 3 cents, Optimism costs 7 cents, and so on. And swapping of tokens also is much cheaper than the $2 here. So the cheapest one is like ZK Sync, which costs like 6 cents. So this is the advantage of using rollups, that there is some initial setup required. You have to first transfer your assets from layer 1 to layer 2, and once you are on layer 2, you can transfer between people on layer 2 at a much cheaper cost. So let me give a classification of the types of rollups which are there. So first there are rollups which use something called on-chain data availability. So DA stands for data availability. And then there are some other technologies like Plasma, and there is also something called Validium, which is off-chain data availability. On-chain data availability means that all the data which is required to generate the state root, that will be stored on the main Ethereum chain as call data, because call data is cheaper. And off-chain is that nothing is stored on the main Ethereum chain. It is all stored by some committee of trusted storage providers. It's called a data availability committee. So Validium is a data availability committee. Validium has a data availability committee, and Plasma has an operator who stores it. As long as you trust the operator, you can trust. As long as you trust them to provide data availability, you are fine. So under rollups, there are two types: application specific and general purpose. So what is the difference? So application specific rollups have limited functionality on layer 2. So L2 stands for layer 2. Like you can say that there are examples of application specific rollups which only support transfers of Ethereum and ERC20 tokens. ERC20 token is a type of token you can create. You will be doing that in the lab today. But general purpose rollups support arbitrary smart contracts on layer 2. So what is an example of an arbitrary smart contract? Maybe you have a voting contract or you have an auction contract. So that is an arbitrary smart contract. That cannot be supported on an application specific rollup. It will be supported on a general purpose rollup. And within application specific rollup, there are three types. One is called an optimistic rollup, validity rollup, and hybrid, which uses a combination of optimistic and validity rollups. So optimistic rollups use something called fault proofs to decide the validity of the state root which is stored on Ethereum. Validity rollups use zero knowledge proofs. They are also called ZK rollups, but the community says we are not using the zero knowledge property of rollups zero knowledge property to ensure validity of the state roots. There is no privacy here, so that is why the name validity rollups is preferred. And hybrid is, it's a hybrid of optimistic and validity rollups. So you will use zero knowledge proofs, but the cost of verifying a zero knowledge proof is high. So you will not verify the zero knowledge proof unless you get a challenge from some user. So examples of optimistic rollups, application specific optimistic rollups are Fuel and Hubble, and Fuel V1, because Fuel V2 version 2 hopes to be a general purpose rollup, general purpose optimistic rollup. Under validity rollups, there are quite a few. There is ZK Sync 1.0, Polygon Hermes 1.0, Loopring, ZK.money, and DYDX. DYDX is runs on something called StarkX, which is a particular kind of validity proof technology. In hybrid, there are a couple: Polygon Nightfall and ZK Opru. So ZK Opru stands for ZK Optimistic Rollup. So that is why it is ZK Opru. It is an Ethereum Foundation project. I put a star there because it has not been launched. It is the code is available online. It is open source, but it has not been launched. So that's why I put a star there. So by the way, the reason rollups are called rollup is that you roll up all the data which is required for some transactions and you put them in the call data. So you roll them up in some sense. That is why it's called a rollup. The first proof of concept was the GitHub repository of that proof of concept had the name rollup, so the name just stuck. So under general purpose, again you have this combination optimistic rollup and validity rollup. And there are the two projects I showed in the screenshot, Arbitrum and Optimism. They are examples of optimistic rollups. And validity rollups are like Starknet, ZK Sync 2.0, Polygon Hermes 2.0, and Scroll. General purpose validity rollups are also called ZK EVMs. EVM stands for Ethereum Virtual Machine. So because the general purpose rollups will support installation of arbitrary smart contracts on layer 2. And the operations done in an arbitrary smart contract has to be verified using zero knowledge proofs. So that's why they're called ZK EVMs, because the operations are on the Ethereum virtual machine. So under the off-chain data availability, these guys, they are not the focus of the rest of my talk, but I'll just list them. So there again you have application specific and general purpose. There are fault proof based or validity proof based. And there is OMG network and Gluon, both of them are Plasma. So there are still some scaling solutions for Ethereum which use off-chain data availability, but the total value locked is not very high. They are not very popular, I would say. The among the application specific rollups which are based on validity proofs, these three are quite popular. Immutable X is an NFT platform. NFT stands for non-fungible tokens. So you can create NFTs on Ethereum using Immutable X, which are much cheaper than creating NFTs using the main Ethereum network. Diversify, I think, is a decentralized exchange, or I don't remember exactly. I think it's a derivatives platform. And Sorare is also a NFT trading platform. So Sorare has a lot of sports NFTs on it. So these are quite popular among the rollups, or these are not rollups. These are technologies which use off-chain data availability. So these three, they use a data availability committee. So the data is not posted on Ethereum mainnet. It's not posted on call data. It is just maintained by a trusted committee of data availability providers, and they sign off saying that we have stored the data which is being whose state root is being stored on main Ethereum network. Then general purpose, there is something called Matrix Andromeda, and there is no general purpose validity proof rollup with off-chain data availability. So the main rollup components are the following. So there is a L1 user wallet. It is like your MetaMask, which I showed in, which is there in your Firefox or your any browser plugin. Then there is a smart contract which is installed on Ethereum called a bridge contract. Then there is the entity who is a rollup operator. This is an entity who will be helping the coordination, all the different parts. The coordination involves communication between the layer 2 chain and the layer 1 chain. And then there is a layer 2 user wallet. So the rollup operator is also called a sequencer or a validator. And what the rollup operator will do is they will expose a RPC endpoint. RPC stands for remote procedure call. So they will have some URL and the port number, and they will say that if you want to do transactions on layer 2, please send me the transactions at this RPC endpoint. So there is no currently most of the rollups they don't have a peer-to-peer network. So in main Ethereum, if you want to send a transaction, you will send it to the peer-to-peer network, and then it will be propagated across the network. But in a rollup, there is a central authority who will take your layer 2 transactions. And then what this operator will do is they will receive transactions from two places. So one is from the bridge contract. So when the L1 users want to transfer their assets to layer 2, they will deposit it into the bridge contract. So the rollup operator will read those kinds of deposit transactions, and they will also read the layer 2 transactions which are sent to them from layer 2 users, and then they will create layer 2 blocks. So this is the L1 deposit. So the rollup operator always monitors the bridge contract for layer 1 deposits. So I have Ethereum on layer 1 on Ethereum. I want to transfer to layer 2. I have to do a deposit first, and then so the rollup operator continuously or periodically monitors the bridge contract which is installed on Ethereum, and it will, whatever deposits it receives, it will transfer those assets to layer 2. And how does it transfer? It will mint those assets in a mint transaction on layer 2. And the bridge contract is just a Solidity smart contract for coordinating asset movement between layer 1 and layer 2. So why do we need some coordination? Mainly to ensure that the state roots are correct, because layer 2 is a separate blockchain. Some hash of the layer 2 state will be stored on the bridge contract. Now if there is a malicious rollup operator, or there is some state root which is faulty, then the bridge contract has to somehow ensure that that faulty state root is rejected. So that coordination is done by the bridge contract. And the bridge contract also receives these layer 2 blocks and stores them as call data. So it not only receives the state roots, which is the hash of this total layer 2 state, but it also stores the layer 2 blocks as call data. And it facilitates verification. So there are two kinds of verification for state roots: a fault proof and a validity proof. A validity proof is nothing but a zero knowledge proof. So the bridge contract will have a verifier operation which verifies the zero knowledge proof in the smart contract itself. And fault proof involves a game between a challenger and a verifier. So I have some slides on that, what that fault proof is. Okay. So what is the layer 2 state? Okay, so this one, okay, maybe I'll show you an example in the case of optimism. Let me switch to my Firefox. So this is the optimism.io, this is the Optimism's website. So here if I go to bridge, it says okay, connect your, so this is, there is a deposit dialog which shows up. I have connected it to my MetaMask already, so my address is showing up here, and it says deposit, it is asking for a deposit, and my current balance is about 1.09 ETH, it's 1.09 Gurley ETH. So it is saying you deposit some amount. I can enter some amount and I can deposit, I can, and it says time to transfer is 20 minutes. So what is this deposit? So what is happening is that this is my, this is the layer 1 testnet. In real life it would be, I would be on Ethereum mainnet, but here in this I am on Gurley, which is the layer 1 testnet. I am going to deposit some amount from my layer 1 testnet to the Optimism, the layer 2 testnet, Optimism Gurley. So let us say deposit. Then it says okay, this is the amount and this is the fees. In current price 0.1 ETH is about $128, and it says time to transfer is 20 minutes. So if I click deposit, then it will ask me to confirm on MetaMask. Then I confirm it, then it will take a bit of time. So it says deposit en route to Optimism. So what is happening in this is that I have layer 1 assets and I am going to transfer it to my layer 2, and once I am on layer 2, then I can do transactions on layer 2. So I will not wait for this because it will take 20 minutes, but I have already done a transaction earlier today. So let us look at deposits. So at 9:43 I had done a deposit of 0.1 ETH. So let me look at the transaction. So here is the transaction which was done about 1 hour 49 minutes ago. So what has happened, the value of the transaction is 0.1 ETH. So the amount of ether which was sent to some contract. So what has happened in this transaction is that 0.1 ETH has gone into this contract. So let us see what this contract is. Before we go there, let us see what actually was this transaction. So this transaction called a function called deposit ETH. If you see this function here, it calls it has two arguments, L2 gas, how much gas to specify, and data, some data, but I think those are all 0 here. They are not, the data is 0, but the L2 gas may be some value here. So that the Optimism bridge took care of these values. Where is the 0.1 specified? So that is specified implicitly. When you send a transaction, if you remember yesterday, there was a value field in the transaction. So the value field will specify how much Ethereum is being transferred along with the transaction. So that is specified in this. So it doesn't need to specify in the function call. So it went to some contract. So what is this contract? Let's look at that contract. So this is some contract which has received many deposit ETH transactions. If you notice, the balance of this contract is 45,712 ether. That's quite a lot of money. One ether costs about, I think, $1,200, $1,200 right now. So it's quite a lot of money. So what is happening is, this is the bridge contract. So when I deposit assets to my layer 2, the bridge contract will hold my assets. So 0.1 ETH was sent to the bridge contract, it will hold it. Then later I may do some transactions on layer 2. Then my 0.1 ether which is in layer 2, some of it will get spent in transactions on layer 2. Then later when I withdraw, then I have to withdraw the amount from the bridge contract. If I want to withdraw my assets from layer 2 back to layer 1, then the bridge contract will check how much money I have remaining in layer 2, and it will allow me to take that amount of ether back onto my layer 1 address. So this is the workflow, or this is like the bridge contract and so on. So let us look at the contract itself. So this, the contract code is not important, but let us look at, so if you want to read this contract, these are the variables which you can read, and then if I want to write into the contract, then it has a bunch of functions. It has deposit ETH which we used, it has donate ETH, it has deposit ERC20, then it has finalize ERC20 withdrawal, finalize ETH withdrawal, and so on. So it allows you to deposit ether, deposit ERC20 tokens, and also withdraw them at a later stage. So let me switch back to my slides. So any questions about this so far? So what is in the layer 2 state? So we said that the layer 2 state, the state root is a hash of the layer 2 state. So it depends on the type of rollup also. So a rollup is a separate blockchain. It is a layer 2 blockchain. It maintains a blockchain of L2 transactions. I can actually show that L2 transactions also. Let me, for optimism's case, let me show that. So let's go to optimism again, and if you go at the very end, there is a block explorer. Let me make this bigger. So this is optimistic.etherscan.io. It is optimism's block explorer. Then there are a bunch of blocks happening here. Let's click on a block. It was 1 minute 30 seconds ago. And then it specifies, it says that the batch size is 144 transactions. It also gives a L1 transaction hash. So what is the L1 transaction? If I click on that, it will open etherscan.io transaction. So optimistic.etherscan.io is the layer 2 block explorer. It shows you blocks from the optimism, the layer 2 blockchain, but the transaction hash on Ethereum scan, etherscan.io, it is a layer 1 transaction. So what is this transaction? Let me make this a little bigger, it's too small. So this was, let's see what this transaction is. We look at the method call. So it says, if you see this, it says append sequencer batch. So sequencer is another word for the rollup operator. It's also called a validator. So this is adding the layer 2 blocks as call data. So if you see this, the amount of data which is being added is quite large. So the call data, which is the data corresponding to all those 144 transactions, that is being sent as call data. So append sequencer batch will have this call data here. If you see that the append sequencer batch has no argument, so the data can be sent as message.data. So transaction, if you remember the transaction fields in Ethereum, there was init/data was one of the fields that has the data which you can send to a transaction. So the call data is sent in that field. So the append sequencer batch itself doesn't need to have an argument for that. Okay. So on layer 2 there is a blockchain, and the rollup operator maintains that blockchain. Most rollups right now have a single operator, so there is a single point of failure, but we will see how that can be mitigated, all the risks of having a single operator. It comes with some risk because the operator may shut shop, they may not be malicious, but maybe they are not able to maintain the maintain operations because their revenues are not enough, so they may close down because of economic reasons. So rollup operators may disappear. So and the rollup operator is the only one who is maintaining the blockchain. So we need some mechanisms to mitigate that risk. So in general purpose, let us look at the layer 2 state before we go to the mitigation mechanisms. So general purpose rollups, again to remind you, you can install arbitrary smart contracts on the layer 2. So the layer 2 state will include the set of all layer 2 accounts and their token balances, and set of all accounts, set of all contracts installed on layer 2 and their code and storage. So it is like a separate blockchain. So if it is a EVM based blockchain, then it will have a copy of, it is a version of the Ethereum virtual machine there. So it will have all kinds of contracts and code and storage and so on. And the L2 state root in this case is the hash of the entire L2 state. So the world state trie, if you look at the root hash of the world state trie on layer 2, that is the layer 2 L2 state root. So in optimism, what optimism has done is they have taken the a Geth is a Go implementation of Ethereum client software. It's called Geth because it's based on Go. They modified it a little bit and they said that we will maintain our L2 state using a modified version of Geth. And the reason it is modified is because it does not, its consensus mechanism is different from the main Ethereum. Geth runs on main Ethereum. Its consensus mechanism is now proof of stake, but on optimism there is no proof of stake mechanism. There is a single operator, and that single operator will just keep producing blocks. There is no need for consensus because there is a single block producer. So they maintain a different modified version of Geth. So basically they remove the proof of stake part out of it, and the L2 state root will be the root hash of the world state trie. In application specific rollups, the L2 state root or the layer 2 state, which is much simpler, it does not have any contracts. So general purpose rollups have contracts, but application specific rollups, they support a very narrow set of use cases like transfers and NFTs. It only needs to express the application state. So suppose I have an application which supports token transfers, then if the application is account based, then a Merkle tree of account balances is sufficient. If it is, and the L2 state root will just be the root hash of that Merkle tree. If the examples are like zkSync 1.0 and Hermes, Polygon Hermes 1.0. So these rollups, they only support transfer of tokens. zkSync 1.0 also supports NFTs, but Hermes 1.0 is only transfer of tokens. Then the root hash is just, the L2 state root is just the root hash of a Merkle tree. But if the application is UTXO based, so UTXO stands for unspent transaction output, then the application state is the set of all UTXOs, like it's like a Bitcoin kind of rollup. But the set of all roots, L2 blocks, set of all L2 blocks is needed to determine the state. Then the tip of the chain is the L2 state root. The hash of the latest L2 block header will be the L2 state root. So example is fuel V1. But in general, the community is moving towards general purpose rollups, because the main reason is that I can have an application specific rollup, but then there is a problem of interacting with other smart contracts. If there are no other smart contracts on my rollup, then if I want to, suppose if I have some tokens on application specific rollups, and then I want to send that token to a contract, but an application specific rollups, there will not be any contracts. So that's why general purpose rollups are becoming more popular. So let's look at a particular L2 state in an application specific rollup. I said zkSync 1.0 is a application specific rollup, and its L2 state is a Merkle tree. So what kind of Merkle tree is it? So the Merkle tree is, it's called a sparse Merkle tree with account state hashes which are leaves, and the account state has some fields. Let me come back to this. So it looks like this. So the state root is a sparse Merkle tree. A sparse Merkle tree is a Merkle tree in which all it's not like at all indices there will not be a leaf. Some of the leaves will be empty. So you will use an index to go to a leaf. If the index exists, you will get a leaf, but some of the indices may lead to a null value. So that's why it's called a sparse Merkle tree. And the state root here corresponds to the hash of a root hash of a sparse Merkle tree, where at each of the leaves you have a hash of an account, hash of account 0, hash of account 1, hash of account 3, and so on. And then what is this hash of account 0? It is a hash of these 4 fields. So each account itself will have a balance tree, which is another sparse Merkle tree, which will have a balance of token 0, token 1. Typically token 0 will be Ethereum, then token 1 can be some popular ERC20 token. So this is called a balance tree. So you take the root hash of this balance tree, and then you hash it with the nonce value, an Ethereum address associated with the account, and some other information. It's called a rescue hash of an L2 public key. I'll come back to this later. So the hash of the accounts is stored in the leaves of this sparse Merkle tree. The account itself has a balance root, which corresponds to a sparse Merkle tree which holds account balances of that particular account. So this is an L2 state of an application specific rollup. I am not showing the NFT part here in the interest of time. So how do you verify state updates? So I said that rollups, they don't store the whole state on layer 1, they only store a hash, a layer 2, a hash of the L2 state root, only store like a 32 byte hash. So how do you ensure that the rollup operator is actually putting correct state roots? What if they are malicious and they put some junk there? So validity rollups, they use zero knowledge proofs to prove correctness of the layer 2 state updates. And Ethereum currently supports zero knowledge proofs based on technologies called SNARKs and STARKs. SNARKs stands for succinct non-interactive arguments of knowledge, and STARKs is, instead of non-interactive, you have T is for transparent. STARKs are also non-interactive, but they are succinct transparent arguments of knowledge. So what does transparent mean? So the SNARKs have involved something called a trusted setup. So people have to generate some cryptographic information before they can generate these kind of proofs, SNARK proofs. But STARKs have no such trusted setup. Because they don't have a trusted setup, they are called transparent. So the transparent indicates that there is no trusted setup involved in STARKs. But what is being proved? So recall the state root I showed in the previous slide. So let's say you have some accounts, they have some balances. The balance roots are stored in these accounts here. Suppose you have a current root R current, and then some transactions happen on layer 2 and you have a new root R new. Now this from R current to R new, what this validity rollups will do is they will give a zero knowledge proof or a validity proof which proves that the transition from R current to R new is correct. So what is involved, what is the input to this proof generation process? So maybe account 0 signed a transaction which transferred for some tokens from to account 1. So account 0 did some transfer to account 1. So when that transfer happens on layer 2, account 0 will give a signature. Now what the snark proof will do is it will prove that I know a signature which was signed by the owner of account 0, and the transaction which that owner signed has approved a transfer to account 1. So the signature will be the input to the proof generation process, but the proof will prove the statement that the root transition from R current to R new is valid. But the input to the proof generation itself will be a bunch of signatures which are signed by the owners of these respective accounts. So the proof pi will prove the correctness of the state root transition, and this proof will be generated off chain. So before that, so this the new root corresponds to the state after executing a block of transactions. So this proof will not be for every transaction, it will be for a block of transactions. So the proofs are generated off chain. So this proof generation process typically is quite compute intensive. So there is people are using GPUs or FPGAs, and there is some efforts to make ASICs for this proof generation process, because currently most of the proof generation happens on the cloud on AWS servers and costs a lot of money. But they are generated off chain, they are not generated in any smart contract or anything. They are generated off chain and they are sent to a bridge contract, and the bridge contract will have a proof verification. The great thing about snarks and starks is that they are asymmetric in terms of the proof generation versus proof verification. The verification process is much simpler and costs much less gas than the proof generation process. So it is done on chain, and the bridge contract needs to have a verifier method to verify this proof. So this is how state updates happen on validity rollups. So any questions about this part?